Hey everyone, and welcome to The Explainer. Today, we're taking a really deep dive into the hidden physics of our everyday lives. We're talking about those invisible, underlying rules that govern absolutely everything, from how you cook your dinner tonight to how massive industrial engines keep from melting down. Let's unpack the mechanics behind heat capacity and specific heat capacity.
Okay, let's dive into this with a scenario we've all experienced at some point. Imagine you make a nice cup of hot tea and you leave a metal spoon sitting right there in the cup. A minute or two goes by, and suddenly that spoon is burning hot. In fact, it feels way hotter to the touch than the water itself, even though they've been sitting in the exact same mug, sharing the exact same environment. So, why does the metal heat up so drastically and, honestly, so much faster?
Now let's take that exact same micro-level principle and scale it way up. Picture a gorgeous sunny day at the beach. The sun has literally been beating down equally on the shoreline all afternoon long. You're walking barefoot and the sand is absolutely scorching. But then you step into the ocean water right next to it and it feels completely freezing. Keep in mind, the sun is pumping the exact same amount of heat energy into both the sand and the water. Yet the sand is burning your feet and the water is taking its sweet time to warm up. To solve the mystery of both that hot spoon and the cool beach, we have to look at how different materials actually store energy. Now, what's really interesting about this is our first core concept. Section 1, what is heat capacity? Think of it as our detective tool for whole objects.
By definition, heat capacity is strictly the amount of heat required to raise the temperature of an entire object by exactly 1 degree Celsius or 1 Kelvin. I really want to emphasize that phrase entire object. When we're talking about standard heat capacity, we are looking at a thing as a complete whole. A whole car, a whole house, or that whole spoon from earlier. The question we're asking is, how much total heat energy do we need to pump into this specific complete object to bump its temperature up by 1 single degree?
And to measure this systematically, we obviously need a standardized unit. The SI unit for heat capacity is the joule per Kelvin, represented as J over K. The joule is simply the heat energy we're adding into the system, and the Kelvin represents the temperature change we want to achieve. Using Kelvin here is super important in thermodynamics because it's an absolute temperature scale. It directly ties the molecular kinetic energy of whatever object we're looking at to a true absolute zero point.
To really visualize how heat capacity behaves with entire objects, just contrast a small cup of water with a massive bucket of water. Because heat capacity cares about the object as a whole, the size of the object massively changes the math. The larger the object, the greater its overall heat capacity, right? If you want to raise the temperature of that giant bucket of water by 1 degree, it's going to require a significantly larger amount of heat energy than bumping up the temperature of that tiny little cup. Size matters immensely when we're dealing with general heat capacity.
Let's move on and see how this builds into our next concept. Section 2, specific heat capacity explained. We're moving from whole objects down to specific masses.
Here is the absolute crucial difference you need to lock into your memory. Specific heat capacity is the amount of heat required to raise the temperature of exactly 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. Notice how the focus totally shifts here? We aren't talking about some random bucket or a randomly sized cup anymore. We are completely leveling the playing field. We take exactly 1 kilogram of water, 1 kilogram of metal, or 1 kilogram of sand, and we test them equally. This lets us compare the inherent, built-in properties of these materials, completely ignoring their overall size or shape. And because our definition just changed to include a specific weight, our unit of measurement has to change right along with it. The SI unit for specific heat capacity is joule per kilogram Kelvin, written as J per kilogram times K. We've literally just inserted kilograms right into the denominator. This perfectly reflects that we're now measuring the heat energy, the joules, needed to change the temperature of one very specific kilogram by 1 Kelvin. It's just a much more precise update to our measuring toolkit.
Now, think of this next formula not as a stressful math test, but just as a very approachable recipe for heat energy. It's Q equals mc delta T. Q is the total heat energy supplied to our object. To figure out Q, you just multiply your 3 recipe ingredients together. M, which is the mass of your substance, C, which is that specific heat capacity we just nailed down, and delta T, which just means the change in temperature. Once you know these variables, you can calculate the precise energy dynamics of pretty much any thermodynamic system out there.
Which naturally leads us to Section 3, contrasting materials, specifically water versus metals.
And this brilliantly illustrates the solution to both of those mysteries we opened with, the spoon in the tea and the sand on the beach.
You see, water has an incredibly high specific heat capacity. It's about 4,184 joules per kilogram Kelvin. It requires a massive amount of energy to budge its temperature. Metals, on the other hand, have wonderfully low specific heat capacities, often just a tenth of water's. So that metal spoon, it gets burning hot while the tea doesn't, because the metal's low specific capacity allows it to absorb energy and spike in temperature super rapidly. And that beach sand burns your feet while the ocean stays nice and cool for the exact same reason.
Let's take this out of the lab. Section 4. Real-world applications. This is how this physics shapes our world.
These thermodynamic properties literally govern the world we live in. Take coastal areas. They generally have a much more moderate climate. Why? Well, the ocean acts like a giant temperature regulator. Water's high specific heat capacity means it absorbs a ton of the sun's heat during the day without drastically changing its own temperature, and then it slowly releases it at night, which keeps nearby coastal temperatures remarkably stable. In engineering, car radiators use water as a coolant for this exact reason. Water can absorb massive amounts of heat from the engine before the fluid itself ever reaches a boiling point. And back in our kitchens, we purposefully make cooking pots out of metal because metal's low specific heat capacity guarantees that heat from the stove transfers to your food almost instantly, rather than the pot just hoarding all that energy for itself.
So the crucial point is coming up right now. Section 5, Summary and Final Thought. Let's quickly wrap up this mystery.
Let's do a really quick review of our key takeaways. First, remember that general heat capacity is the heat needed to raise the temperature of a whole entire object by 1 degree. Second, specific heat capacity scales that down to equalize things, measuring the heat needed for exactly 1 kilogram of a substance. Third, remember our contrasting materials. Water is stubborn. It has a remarkably high specific heat capacity, making it a slow heater and a slow cooler. Metals are eager. They have a very low specific heat capacity, making them heat up and cool down incredibly fast. And finally, these concepts aren't just textbook theory. They control our cooking, drive our engineering, dictate our daily weather, and run massive industrial applications.
We've talked a lot today about teacups, sunny beaches, and car radiators. But I really want you to look around you today. Beyond our kitchens and coasts, how else does this invisible force of specific heat capacity shape the world you interact with? Every single time you feel a breeze or turn on a machine, this dynamic exchange of heat energy is hard at work behind the scenes. Keep observing, keep questioning the amazing physics of your daily life. Thank you so much for joining me for this explainer, and I'll catch you for our next topic.